Hi everyone, thank you so much for joining Space City Rocketry for our critical design review, where you will be getting a sneak peek into this year's project cycle. So, my name is Shrishti. I'm the project manager for Space City Rocketry, the 2025 and 2026 project cycle. I'm going to be starting off with giving you guys the agenda or just things to expect for this upcoming presentation. We're going to start off with team introductions, where you guys will learn more about our team. We're going to move on to team goals and an overview of Juno, this upcoming year's launch, where you can learn more about our budget and as well as our previous experience from previous launches. Then we're going to be moving on to analysis, where you guys can learn about this launch's preferred software, our flight and structural predictions and review. Then next we're going to be moving on to propulsion, where you will learn about our new motor selection as well as our reasoning for said motor selection. Then we're going to be moving on to structures, where you guys will learn about structural design, verification, and implementation. Next, we're going to be moving on to avionics, where you guys will learn about our flight computers and avionics' new plans of launching this upcoming project cycle. Then we're going to be moving on to recovery, where you guys will learn about recovery's new dual bay design as well as their ejection plans. Next, we're going to be introducing something new this upcoming time, a test launch, where you guys will be finding out our reasoning as well as a timeline for our test launch. Then lastly, we're going to end our critical design review by having or hosting a questions and answer session, where you can ask us more about our project and get more depth review about it. Lastly, even though this isn't specifically for our CDR, we do have a section in the slides labeled Appendix, where you can learn more about our projects, such as formulas used, specific calculations, Gantt charts, as well as specific electronics. So I'm going to be starting off with team introductions. So again, I'm Shrishti, the project manager for Space City Rocketry. This is Dita, our chief engineer. Moving on to our sub-team leads, we have John, our recovery sub-team lead. Then we have Matthew and Hector, our two structure sub-team leads. Then we have Liv, our analysis sub-team lead, and Nathan, Jake, and Thon, our three avionics sub-team leads. Again, this is just another description of our team structure as well as sort of leadership hierarchy. We also have, in addition to our structure in the slide, our two mentors, Doug as well as Randy, and Randy also being our flyer of record, as well as our UH faculty advisor, Dr. Braxavanis. Then moving into our demographics, as you can see on the left, we have the same demographics as presented to you guys from PDR, the classifications, as well as our gender distributions, as well as our ethnicity distributions. But this time around for CDR, we decided to add in more, such as our certification distribution. So currently we have 12 people who have completed their L1 certification on our team, with 9 progressing towards their L1 certification. We have 2 people that have completed the L2 certification, with 8 progressing towards their L2 certification, and we have 1 person currently progressing towards their L3 certification. Then moving on to ham licensing, we have 4 people in our team that currently hold ham licenses, and 2 people in our team that are aiming towards getting their ham license.
So, for a little bit of history on Space City Rocketry's background, last year we competed in the 10K commercial off-the-shelf category at IREC with Phoenix. We did face some significant challenges, especially with the uncertainty of the launch site location, as well as some changes in leadership that took place. Despite all this, the team was able to successfully get to Midland and launch the vehicle. Unfortunately, in our recovery, we were not as successful. However, we were able to recover our payload experiment, and with that we won the first place in the SDL payload challenge. So for an overall timeline, since PDR, we've been working on implementing and reviewing our feedback that we got, and that led to some refinements in the design and some minor changes. Leading up to CDR, which is today, we have begun some manufacturing tasks for Juno. Following CDR, we will be reviewing and implementing the feedback that we get from CDR. We will then progress to completing manufacturing by late March to early April, and with the goal of competing at Midland in June on the 14th. So changes from PDR and the current state of Juno. So all of our airframe parts have been ordered and received, as well as our motor and its associated hardware have been ordered. We have begun cutting and squaring the airframes and couplers, and we are still evaluating potential experiments for the SDL payload challenge. We have set an internal team deadline for March 25th. So for our budget, the team has spent around $3,800 so far, and we anticipate needing to spend another $780 on the actual rocket. The remaining spending that we have is around $2,880, and almost all of that is competition costs. That's dominated primarily by the lodging expenses for 7 nights, 3 rooms for 8 peoples, and the $700 rocket fee. We currently have $2,428 in the bank, and we anticipate needing another $800 and $840. That is our baseline budget. We do have an ideal budget or ideal case, and that includes an additional room that adds around $600 to our overall need, which brings it up to $1,435. Moving on to analysis. So, yeah. For an overall view, or starting with an overall overview of Juno, Juno is a 6-inch diameter rocket with a total length of 117 inches, which is a little under 10 feet. It has a dry mass of 39.2 pounds and a wet mass of 69.3 pounds, and that's including the motor and all associated hardware. We have 2 main internal coupler sections that carry a lot of the important items that we have. The payload coupler, which is 12 inches long, it contains the CubeSat for our payload experiment, and it weighs 11 pounds. The avionics coupler, which contains all our flight computers and associated hardware, is 14 inches long and weighs around 9.5 pounds. The 2 couplers are where we've decided to add our variable ballast to tune our stability and tune our apogee. So for a breakdown of the overall competition scores, there is a total of 1,000 possible points for the competition, along with an extra 50 bonus points for adopting the CubeSat form factor for the payload experiment. So breaking down those 1,000 points, 60 of those are awarded for the timely submission of competition documents. 440 points are split between the technical report and the design and build quality, and the remaining 500 points are focused on flight performance. So breaking down that flight performance, that 500 for the flight performance a little further, there's a 150 point reward, or 150 of those points are are awarded on a binary basis. So for recovering the vehicle, so if the vehicle is successfully recovered with no damage or is reflyable, that the team's awarded 150 points. If that is not the case, then that category, we receive a 0 for that 150 points. The remaining 350 points are for apogee accuracy, and that requires a bit more analysis in its approach. As the formula shows above in the top left corner, we lose around 0.1 points for every foot in apogee we deviate from our 10,000 foot target, and a 3,000 foot deviation will result in 0 points being awarded for that specific item. To kind of plan around this, we've developed a competition score optimization sort of analysis, and you can see that on the right there. And that essentially is based on a 1D simulation, which allows us to visualize different configurations for the ballast in the payload coupler and in the avionics coupler, and how that will affect our scoring potential. Basically, how close to 30,000 feet to 10,000 feet we can get. This is not the end numbers we'd be using, so this would serve as a launching basis point for plugging these numbers into our 6 degree of freedom simulation softwares. that are a lot more accurate and take into account a lot more things. And it helps us ensure our flight day weight adjustments are grounded in simulated performance rather than just simple estimates. So here we have those 6 degree of freedom simulation softwares mentioned before. The three are OpenRocket, ROS Aero 2, and RockSim Pro. Overall, the apogee numbers are very close to each other, so they're all within 5% of each other. Differences in acceleration and maximum speed come from how each software handles the aerodynamics and drag modeling of the vehicle. For across all three softwares, we've kept our simulations with consistent baseload assumptions. So a 6 degree launch angle, the same site elevation of 890 meters, and a zero wind. So this is intentionally including a roughly 2,000 foot buffer in our targeting to leave margin for real world effects on our potential apogee loss. Yeah, our stability is across all three softwares is around 2 calipers. So once we get closer to the launch, we will update these simulations with more up-to-date masses and weather expectations. That will help us further refine our simulations. Moving on to propulsion. So we have a few main criteria for our motor selection. The main one is the minimum off-the-rail velocity, and that is set by the competition to be a minimum of 82.5 feet per second. And that's given an effective rail length of 14.5 feet. That is essentially the point at which the vehicle only has one rail button still on the rail. So that's 14.5 feet for our vehicle. So our motor must additionally give us enough overshoot on our apogee to give us margin in the event that just through general manufacturing, the vehicle ends up weighing more than what we kind of assumed for our baseline simulations, as well as to account for weather conditions on the launch site. And kind of the reasoning behind that is that it's a lot easier to add weight to reduce the apogee than it is to kind of try to scramble to reduce weight to increase the apogee. So during PDR, we presented the M4500 Super Thunder, and that gave us around 300 feet of additional apogee. However, a slight change in how we were constructing the fins based on our feedback from PDR resulted in us losing around 600 feet to around 9,700 feet. And that kind of plays into that. It's a lot easier to add weight to reduce apogee than it is to lose weight to increase it. So we just decided to select a more powerful motor that would give us a lot more margin to kind of play around and not have to worry as much regarding the reducing weight thing. So presented below, we have a table of around 8 motors within the M impulse class that kind of fit our needs, and we have around 3 of them that meet our minimum off-the-rail velocity. The M4500 is the one we presented at CDR, as I previously mentioned. The other 2 are the M6000 and the M2500. So we ended up going with the M2500 as it met our minimum off-the-rail velocity, and it gave us around 2,000 feet in overshoot on our apogee, and that would allow us to accommodate just variability in the wind on launch day, as well as just general design choices. For the M6000, the reason we decided against that one and chose the M2500, while they both met our minimum off-the-rail velocity, the M6000 gave us a lot more overshoots. It overshot by around 3,000 feet, so that would require a lot more mass to add to the vehicle to get it down to 10,000 feet. So, yeah, and the motor was ordered and it will be picked up at the designated shipping location at Midland at the competition. And we'll pass it off to structures.
weld nuts along the coupler, and then we will have 9 1032 hexbolt black oxide screws radially to secure the coupler to the upper airframe. Okay. Here you can kind of see the arrangement of the components that I have on the CAD. Now some things may change slightly as avionics make further decisions as how they're going to do wiring and things like that. But a lot of this is adjustable as we can change up where the holes are going to be, so we can do the threaded inserts and maneuver parts around. But as you can see, we have our screw switches, we have our batteries. Then black on the left is the camera, the run cam, thumb cam 2, which will have a pinhole camera as well. Then you have the telemetrum and the easy menu as well. As far as the payload, so it is still going to be we're going for the CubeSat design. We have a 3D printed frame as well as a 3D printed sleeve, so it'll kind of all go together. As far as the ballast weight for it, because we are going for a ballast right now because we haven't had an experimental payload designed yet. If we do one, so we're aiming for a ballast. The ballast will be pretty much squares with varied infill, so we can reach the desired weight that we want. If we need to add weight, we can add it for ballast without affecting too much of the stability. So it's pretty simple. again with the U-bolt and the threaded rod design. Here we kind of have a little bit about our screw analysis. You get a little bit of an overview, as well as where the screws will go on the avionics and the nose cone section. As far as the analysis method, we have uh, a screw calculator. We identify the relevant masses as well as the forces on the actual rocket, estimating impact that it will come down on, snatch forces. So we work with the recovery on that as well. We take the largest force that the bays and components will have exerted on them, and then we distribute them along the screws, and based on what it is, which most of these are going to be shear, we get that calculation based off the tensile strength of the screw itself. As far as the screw analysis, you can kind of see the avionics one right there. Total, it's going to be around 18 pounds. You see the largest force of impact. And we're aiming for a minimum factor of safety of 2. And with nine screws, we exceed it and get a true factor of safety of 2.2 as well. As far as the payload, it's a little bit less force, around 3,000 pounds of force. And it is also lighter, around 12 pounds. And with 6 screws, we achieve a true factor of safety of 2.21. And then here we have the recovery hardware. On both ends of the avionics bay, the recovery hardware is attached to the bulkheads, as well as the U-bolt is to secure all of the lines and everything that John will tell us more about as well. But it's simply attached to the bulkhead, drilled holes so wiring can go through, as well as all of the charges.
In terms of our motor retention system, we'll be using a 98 millimeter AeroPack retainer. We'll secure this through the rear centering ring, simplify our manufacturing, and just ease. We decided not to go with the front motor retainer bulkhead and just use an eye bolt threaded into the front closure of the motor. We wanted to place ballast. We wanted to place ballast on top of this front bulkhead just because it's a somewhat convenient position, but we decided to move the ballast into the avionics and payload for greater versatility. And our fins are going to be 3/10 inch thick with 5 plies of carbon fiber on each side, 10 plies in total. We will be going for a semi-quasi-isotropic layup with 0 degrees, positive 45 degrees, 90 degrees, minus 45 degrees, and 0 degrees to balance out the load properties and to prevent the prevalence of weak planes. We'll be assembling this externally and then bond it to the motor mount tube. To sandwich the fins and make them more secure, we will be putting them between the forward and rear centering ring, and we will be doing this structural bonding with Proline 4500. Our core materials are fins, as we mentioned, is 3/16 inch G10 fiberglass, and some of the laminating materials we have mentioned. Some of the laminating materials we have considered are intermediate modulus 6K carbon fiber from Composite Envisions, but we are only able to have used it for our first coupon set, as we have unfortunately run out. In light of this, we are considering a new carbon fiber of similar modulus from Solid Composite that weighs roughly 11 ounces per square yard. And for comparison's sake, we also did some layups with 6-ounce fiberglass. For our epoxy system, we'll be using System 2000 from fiberglass with the 2120 hardener. And terms of our layup procedure, we'll be taping and labeling the cloth in what order we're going to lay down the plies. And then once we do that, we will sand the core and see how good surface tension is for receiving epoxy through a water bead test. And once we do that and see it's acceptable, we'll clean it off with acetone and isopropyl alcohol and then do our layups, apply our peel ply, breather and vacuum bag it, and then for ideal curing of our long cure epoxy, we will keep it in a stable temperature.
Yeah. Doesn't even let me. Is it on here? You want to mess with it?
We will see. See,
Oh, let's go.
How many engineers does it take?
Okay.
While laminating the testing coupons, we have learned a few lessons. Carbon fiber is visually harder to tell when it's fully laminated because it does not have the same transparency as fiberglass. In one of our coupon sets, there was a partial delamination failure when we tried cutting it out. So we definitely need to make sure our epoxy is applied evenly and there's no voids or bubbles. Labeling and keeping them sorted definitely saved a lot of time in coupon manufacturing. We did it in only a few hours. And as we said, our taping and using electric shears also saved time and effort. Okay. I think you skipped 2 slides. In terms of our fin material, explaining it in a cost sense, carbon fiber we have been using is 2x2 6K intermodulus weave from Composite Envisions. However, the price per yard is now $64. That is about 3 times than it was about a year ago. Just for reference, it's 9/1000 of an inch thick per ply. And I guess for more conservative estimate, we expect to use at most 1.5 yards of fabric this year's competition cycle, but for a good margin, we want to get at least 3 yards. Instead, we could get a cheaper fabric from solid composites of similar modulus, but with slightly greater thickness of 14/1000 of an inch per ply. In doing so, we can save $120 in material cost by switching to the similar fabric. In terms of matrix properties of our fins, for the original fiber, tensile modulus 40 MSI. Fabric from solid composites intermodulus to weave has a tensile modulus 43 MSI. Volume fractions are expected to remain rather consistent as we're using vacuum bagging to consolidate our layups. Given the increase in modulus, we expect our fin stack to be somewhat stronger. Safety factors of our fins should not decrease as higher modulus allows for a higher flutter threshold. For terms of our epoxy system, why we're using it, compared to other conventional systems such as West System, Total Boat, US Composites, Fiberglass System 2000 has a much higher glass transition temperature, which is good for handling in the sun, and also has much greater material strength. One issue we did face, as mentioned in manufacturing the coupons, was that they were tough and difficult to shape. As in the pictures, you can see how many difficulties we had, especially with breaking saws and similar blades. To get past this, we changed our cutting approach to go slower and use saws and tools more appropriate and which are less likely to break. including water cooling, and just aiming for a good sample. But through this, we have managed to complete our practice samples and ready for destructive testing.
Well, there's them cutting some of the coupons. This one over here. That's cutting with, or that's cleaning the blade, I guess.
No, it's actually cutting with the water spray.
Oh yeah, cutting with the water spray. And then more cutting. It was a lot of work. There you go.
As a direct test to determine our shear modules, we'll be using test coupons made of the same base G10 fiberglass and the same layup style we plan to use for our competition fins. There are 3 additional sets of fiberglass coupons with varying layup styles. Of those 3 sets, one is made as a control to determine the approximate strength of the banded carbon fiber. In this, we will have the same layup orientation as the competition fins. To empirically determine the shear modules, we'll be using 3-point bend testing. Seeking materials testing, we have reached out to Dr. Hamami, who works with materials science and MAE. Main reason we are doing so is so we can support and facilitate our testing, validate our hand calculations, find a good setup to complete the test. It's important to include this for our technical feedback and actually see that our assumptions translate to the real world, our calculations. So far, we have cut down our airframes from the original manufacturer size of 60 inches and 30 inches to 56 inches and 28 inches in length. The ends are squared, and we are preparing to extend the fin slots so we can slide the whole fin assembly when it is complete and prepare the centering rings for bonding sometime.
So, as you see on here, and Doug over there, he designed actually this squaring tool. Previously, my method of squaring last year was a little bit tedious, involved a lot of spinning of the airframe on the floor with flat surface, and making sure it was square. However, with this that Doug came up with, it pretty much just goes on the end of the airframe, and then you just spin the drill and it sands it down square. The biggest thing whenever it comes to squaring airframes is whenever you put on the coupler, whenever you push the airframes together, you will have like little or no gap. And it's just about better and just general build quality, especially whenever you're putting sections together and trying to line up screws and things like that. As you'll see, you'll see the airframe work we've done. We did that last Sunday, at Doug's place. So as you can see, we actually got the airframes all put together and squared, and as you can see, it's pretty cleanly attached together. So definitely a lot of progress in terms of the airframes. Now we can actually start working on the fin assembly, manufacturing the fins, getting that all together, and then move forward as well. What's this?
Plan for construction for pre-phase and phase 1, splitting into several phases, pre-phase to phase 3. Our pre-phase includes finalizing the ballast plans, doing our screw analysis, creating jig models, and creating our layup procedures. For phase 1 and phase 2, our test coupons are created for strength testing, cutting down our airframes and squaring them, extending the fin slits, and preparing the motor mount tube for root bonding and subsequent bonding to the aero pack. Cutting out our fin profiles from the core plate and then doing our layups on them and cutting them down to their final shape if needed, mounting the fins to the motor mount tube and to its eventual place in the lower airframe. For the phase 2, we will drill holes and bulkheads for a U-bolt, threaded rod, print the vein CubeSat frame, set up our 3D prints, mount up electronics, and test our ballast, our recovery hardware as well. For our final phase, phase 3, map out our radial holes from our center line jigs and drill our coupler mounting holes, shear pin holes, vent screw and camera pin holes, mounting our internal weld nuts to secure our couplers, drill our holes, mount throw buttons along the airframe. Lastly, prepare our airframe for painting and subsequent finishing.
As far as what's left before flight, as you saw a lot of our manufacturing plans, but in general, finish and confirm screw and hardware implementation. Most of it is pretty much already done. It's just about purchasing and receiving those materials and getting things put together. Completing coupon destructive testing. We did already speak to Dr. Mami about getting that scheduled, so pretty soon that should be happening. Finalizing the install of the ablaid sled, payload housing, getting those 3D printed, and making sure we can do those final changes that we need. Manufacturing fin assembly and assemble airframes around that. Continue integrated dry runs, recovery interface checks, and then ground testing supports before we can actually assemble everything and get ready for flight. And moving on to avionics. Thank you.
So hello, my name is Jake Rodriguez. Sorry. Yeah, you good. Have you good?
Oh, Nathan. My name is Tan. I'm junior electrical engineering.
Yeah. I am a sophomore computer engineer.
I'm a junior.
And we are the avionics sub team. So just kind of give you a quick overview of like what we do and what we are in charge of for the system is that we kind of electronically detonate the charge and collect telemetry data from our 3 flight computers. The first one we use is referred to as COTS, as commercial off the shelves. Those are our primary and secondary flight computers. Those are the ones who actually deploy the charges. We track them using 70 centimeters. I'll go more into that later. And then we receive the data from the ground. And then our secondary system is our SRAD system, which is the student research and design system. For student research and design, we develop our own software and the PCB boards. For that system, all it does is just collect telemetry data. We also develop a ground station so we can see that live telemetry as it's crucial information to recover the rocket. And if anything goes wrong, we have that data so we can analyze if we need to. 40% of the proposed system is SRAD. It's very simple to kind of implement the COT system as it's just purchased and just kind of refining, where most of our work is the SRAD system as it takes a lot of development. Kind of the goal this year was to build a robust computer methodology because, we have a strong knowledge base within our system and we just want to further inform people in the future and actually create this strong system where we can further the knowledge of our team and create a good system. So this is kind of the overview structure of kind of how it works. We have the onboard flight system, which separates into the COTS flight computer and structures and the SRAD. And then we have the ground system, which is the ground station and software, and then the telemetry, and then the ham radio as well. So to go into the first flight computer, our primary one is a Telemetrum 4.0. It has dual deployment, meaning that we have we have a apogee and a main charge, and both of them will go off at different times. One will go off at apogee, and the second one will be a second altitude determined through analysis and just validation. It has onboard non-volatile memory. It has onboard live data logging, and has a barometric pressure sensor that works up to about 100,000 feet. It has a one-axis 200G accelerometer and an onboard GPS. It does use the 70 centimeter hand band, which is a requirement of our competition, and it is a technician level requirement for our hand license. It uses a 3.7 Li battery, and the dimensions and weights are there. Our secondary flight computer is a Easy Mini. It also has the same dual deployment capabilities and has non-volatile memory and live data logging, and has a barometric pressure sensor up to 100,000 feet, but it doesn't transmit data. It kind of just saves it internally as a backup system, and just kind of stores it. It also uses a 3.7 Lion, and this is just our backup system to if for whatever reason our main flight computer doesn't work, will blow up a second set of recovery charges to make sure that our parachutes will deploy. Kind of go into the reasons of why we chose these flight computers. The telemetrum, like I mentioned, meets the 7 centimeter band requirement for the COTS GPS. That's a new rule. They found a lot of interference with the 33 centimeter, so we are required to kind of switch to a 70 centimeter. We've already had experience with this flight computer before, so we kind of chose to keep with it, and it has shown good results so far. And also just combining the altimeter and GPS that one uses is a great thing for ease of integration. Easy Mini is just because it's a basic and simple barometric flight computer that fits our needs as a full redundant flight computer. I will mention testing on this one later, but Easy Mini is a very staple for beginning rocketry, and a lot of people use it. So it's a very trustworthy and has been proven to work very well. And it uses the same software interface as our primary flight computer. Both uses Alt OS as its ground station and its setup. So kind of going to the tertiary system, which is our SY flight computer. It uses a dual core microcontroller. It has all sensors running on ITC or SPI. We developed a new PCB from the ground up. Just because we lost a lot of the PCBs from the year before, and we had to kind of switch, and we wanted to switch over to a different microcontroller. So we designed our own PCB from the ground up as well to kind of do it. We kept the same stack design, which is basically layered PCBs. Which means that we have the bottom one being the main flight computer, goes into sensors, and then goes into telemetry. This way, it fits within our design construction of about 6 inches inside the AV bay, as it would be a lot bigger if we try to put it into one board. It does not do pyro, as there was going to be a lot more testing, a lot more integration with that, and we just wanted to make a good board that can save and transmit data. Software is kind of a refined and refactored pieces of legacy cell code. We have used code from last year's rocket, but we have been refining it and making it better. And then data will be saved through an SD card through a breakout board, but we have been talking about maybe possibly also storing that data into internal flash memory as well. Like I mentioned, it will be sent to the ground through a 70 centimeter LoRa module to kind of keep within that non-interference range of IREC of keeping away from that 33 centimeters. And we are planning on doing some interference tests, but we have talked to people about how we can make sure that we're not interfering with each other. Also, they will be in different frequencies, as we will discuss later. The final thing I will mention is going to be using a 2S 7.4 Li battery. We have found that this board kind of takes up a lot of power, and so we kind of upgraded it so that everything kind of runs on 5 volts, at least in terms of the microcontroller and 2 sensors that we will discuss later. So the main board we decided on was an ESP32 S3. This is kind of the most powerful ESP32 that is an actual development board. The reason we chose this one specifically is kind of with its dual core capabilities. We have enough headway of frequency, it goes fast enough that we need. It has enough GPIO pins, and the size is perfect for what we needed. The main reason we kind of went for a dual core is that we found GPS to be very intensive. It kept on slowing down every other sensor, so we wanted to put that on a separate core. And so we ended up deciding to kind of put them. So we ended up doing the dual core design, and we'll talk about how successful that has been in terms of software development in a second. These are our sensors. I will say there is an appendix slide with all the data, so specifics on how these kind of work. But we have a BMP 581, which is our barometric and temperature sensor. So it detects pressure and also tells us what our altitude is. The LSM is our accelerometer and gyro. It is our lowest end but more accurate gyro. It goes about plus or minus 32 Gs. So it's a little bit lower range, but it is like a very more accurate accelerometer. And then we have a high G accelerometer that goes up to 200 Gs. Less accurate, but if in the future, as this is a progressive system, if we ever went above the 32 Gs, the 200 Gs will be able to track the rocket for the whole flight. We have a mini GPS, kind of runs on the same type of GPS structure, about 33 channels as last year, but the difference is that it runs on ITC versus UART, as that is a faster protocol to kind of use. Runs about 5 hertz. A Briano, our absolute orientation sensor, just kind of has it has 9 degrees. It says 9 degrees of freedom. We can talk about that one later. But it kind of just tells us like what the orientation of what the flight computer and the rocket is going to be. And then this is our lower module, the one that transmits 70 centimeters out to the ground. So the hardware deliverables from PDR are we were going to improve the PCB to include power delivery, SD card, and a RTC, battery drain test system, and then work towards a final prototype to get ready for a test launch. And what we have done so far is that we have finished a second prototype that adds SD card, power delivery, and RTC and into it. The asterisk is kind of like we have it and we have the plans for it, but we ran into some like software issues that we're trying to develop and trying to make sure we can fix. But the board is kind of aligned, and I'm kind of just talking to my software developer to make sure like everything's finalized. The board isn't ordered yet, but we have the plans there. Upgraded the system to 5 volts, like I mentioned. This kind of goes back to the SD card and power delivery issue that we kind of ran into where we needed more power. So we kind of went to a 2S Li-ion battery that went bucket down to 5 volts. We finished basic battery testing for the COTS flight computer, and we are on track to finishing the prototype by test launch. Future tests, just refining the SRI flight computer for the final design, verify the telemetry setup, just make sure everything works within the AV bay that we have and everything, we can receive data and everything's great, and test flight the SRI flight computer during the test launch in April. And so now we'll go into software.
I'm gonna come do the slide. So I'm Nathan. I'm responsible for the flight software this year. So I want to start by saying that the flight software is out on GitHub. If you have any questions that I can't answer today and you feel so inclined, there's a link here in the slides that you could take a look at. We continue to develop it in the open with the members that are contributing. But obviously feel free to bug me. So a little bit of some architectural decisions we have here. We use C for our software and C++ where necessary. C is kind of the language of choice for embedded systems programming because it allows direct and convenient hardware access, and it's extremely fast and low overhead, right? So it runs very well on small processors. C++ is mostly the same. We have to inherit C++ from some of the sensor drivers that we're currently using because that's what they're written in. And kind of like all squares are rectangles, but not all rectangles are square. All C's can be C++, but not all C++ can be C. As far as the hardware interfaces go, we're working with the vendor-supported ESP IDF board support package and hardware abstraction layer, and we've hooked in a little bit of the Arduino framework to make the sensors compatible with that. And then all of our member-developed software runs inside a free RTOS port that runs within the ESP development environment. And we'll talk more about that later. So yeah, I mean, the goal in general of the computer this year is not really to, I guess we haven't formed any opinions yet, right? We're trying to provide information to form opinions, right? So we're really collecting data during flight. We want to kind of know which stage of flight the rocket is in. We want to keep a record of that data and then redundantly transmit it to the ground. So yeah, I guess goal number one is that we're not biting off more than we can chew, that it's telling us things that we would want to know for the future, right? If we have any more specific goals, then we have a large trove of information about what might work, what doesn't work. We try to collect data, make decisions about what that data means, and then do nothing with it for now because the computer's not plugged into anything. But we collect all the data with even priority, right? We're not saying we have speed. We could collect this data more accurately, more quickly than this data at the expense of something else, right? They're all kind of evenly optimized. And then if we can validate that the computer can make any kind of determinations of flight state, then we're ready to use it when the team is ready. We also like to transmit the data to the ground over a LoRa antenna. This is expensive and difficult and often unreliable in practice. So we do it. We do not do it as often as we save to disk. Not all data is transmitted to the ground. And then flight state determination is a state machine. Right now, basically, it listens for data spikes in certain areas to determine like, oh, okay, we've launched, or maybe we're not launching anymore, right? And then the last kind of component here is fault tolerance, right? If something goes wrong on the hardware side, there's a balance of what we can do in software to detect that and what we shouldn't really do in software to detect that, right? And we try to optimize that as well. So aside number one, why free RTOS? Why not just the plain ESP IDF, or if you're familiar with Arduino boards, they have their own development environment that's convenient and easy to use. Well, first, what is an RTOS, right? So an RTOS is a real-time operating system. And a real-time operating system is designed for time-constrained tasks with hard deadlines. And a hard deadline is that if you miss this deadline, something fails completely. There's no recovery, right? So Windows or Mac OS is a general purpose operating system, and every time you run a program, there's no deterministic guarantee of how long it'll take. But those kinds of systems don't work in things like cars or rockets because you have to press the brake pedal and the car has to stop the same amount of time every time, right? So using an RTOS kind of allows us to make deterministic claims and goals about what our software does. So why free RTOS instead of commercial options? Well, free RTOS is free. It's open source. We can put it anywhere, use it in anything. And it's very lightweight. It is just a scheduler, right? It just allows us to make those deterministic guarantees. And it doesn't make any assumptions about the hardware. So we take care of that with the vendor package versus baking that into the RTOS. Which means that if we ever use different hardware or an integrated circuit in the future looks different, this software will still run on it, right? We only have to worry about the hardware layer, not the RTOS layer. So yeah, I kind of said the quiet part out loud here about the third bullet, that it's hardware agnostic and valuable for future designs. So at PDR, we promised a few main things, right? The first one was a number of scheduling deadlines, right? We promised at least a 5 hertz GPS update and a 5 hertz transmission of data. That is a hardware bottleneck. The GPS chip, both this year and last year, actually, as it turns out, cannot transmit, or they cannot get new readings faster than 5 hertz. They can output data at 10 hertz. It's just two values of the same data. Not sure why that's useful, but they tricked us last year. So now we're running at 5 hertz. And as a minimum, a 50 hertz read of all the other sensors, which are mostly inertial and altimeters, right? And we want to save, we also promised that whatever data this generates will be saved to non-volatile memory, meaning that if the computer lost power or we crashed, we wouldn't lose the data, right? With no performance impact to the sensor reading, right? So there's no weird hiccups over time as we try to read off data. For the state machine, we at least promised that we would detect landing and launch, right? Maybe we would detect apogee, and we said, okay, if we're getting really ambitious, we can get into filtering and some sequential state estimation, but unlikely we'd get there, but possible with enough time. For fault tolerance, we said we would check each sensor when the board turned on. We would make sure that if the board powered on in the rocket and one of the sensors wasn't working, that would not destroy the state machine. We have redundant sources of information from all of our sensors, and so it would just use the one that works but is less accurate or not preferred for some reason. And then possibly even check every time we talk to a sensor, is the sensor even on? Or are we doing something wrong here? And So fast forward to now, we have hit this 5 hertz scheduling deadline. We have hit this 50 hertz scheduling deadline. The data is saved off to non-volatile memory with no performance drop. For as far as the state machine goes, we can detect landing and launch. We can detect apogee, at least with software and kind of tests, but hopefully we will be able to demonstrate that with a true test flight. We've also gotten deeper into sensor calibration, which turned out to be a bigger rabbit hole than we imagined it would be at PDR. And it's unlikely that we would have time to implement something like a Kalman filter before test launch, right? As far as fault tolerance goes, we are doing the sensor initialization checks. The state machine will use the most optimal available data. We're probably not going to validate every sensor read. The likelihood of the board of a cut trace PCB failing on launch, if it hadn't failed earlier, is extremely low. It was a high data overhead for us, and we didn't really have the transmission bandwidth. So at that point, if something breaks while the rocket is in the air on the PCB, we've already had bigger mechanical and structural problems. So aside number 2 is the software scheduling. Aside from testing the code, how do we know that the system actually works, right? So aside from identifying which things take the longest, right? The 5 hertz transmission actually revolves around the 5 hertz GPS update. There's actually math here that shows us we can do this or this will work, right? So the kind of schedule that we've picked is rate monotonic scheduling, right? Every task will run at some period and then take some amount of time. We also modify this model a little bit to use preemption, where each task is given a priority, and if a higher task becomes eligible to run while a lower priority task is running, it will go first. And this is kind of the formula that gives you a lower bound on rate monotonic schedulability. So U of I is the sum of all of your CPU utilization, and if that where n is the number of tasks here, if that's less than or equal to n times 2 to the 1 over, right, then your system is for sure schedulable. You can tweak some rules and break some rules. It's just a math model. It doesn't really account for hardware as much, and you can actually kind of break that rule and go higher. But if you're under this bound, your system is schedulable. So here's what the test shows. We use the hardware CPU timers to kind of benchmark operations in microseconds where possible, and milliseconds where not possible. And we've got our tasks split up between cores, right? So FreeRTOS was a software optimization. Dual core also allows us some kind of asynchronous optimization, right? And at the end of this, when you sum this all up, the first core is only 16% utilized, right? Only 16% of the available processor time is utilized. The second core is only 7% utilized, right? So we've got the software as lean and mean as possible in the computer and structured in such a way that there's tons of leftover processing power for more projects, or, saying, well, we said 50 hertz, maybe we could pull off 100 hertz, right? So yeah, so now we're moving into state machine and calibration. Basically, the sensors have to be reasonably well calibrated to make the state machine mean anything. If there's no expectation that the sensor data is correct at all, then the state machine is useless. So we really prioritized IMU calibration and altimeter calibration here. So for IMUs, we want to calibrate the static bias noise when we power on the computer using an online algorithm. Basically, an online algorithm, like imagine you're taking the average of 20 numbers, and then now you want to take the average 21 numbers. Do you want to have to add them all up again and then divide by 21 instead of 20? Not really, right? And then you have to save all your old numbers. So an online algorithm updates that in place sequentially. So all you need is your previous state and your next measurement. This allows us to kind of tweak and tune our calibration length and duration. We've selected Welford's online algorithm for this because it calculates running average and variance simultaneously, right? So if let's say we power on the computer, then we move the rocket around on the stand, right? The variance will balloon pretty quickly. The calibration procedure will recognize that and just restart, because after we're done screwing with it, it's going to sit on the launch pad for probably a couple hours, right? That's beautiful calibration data time. As far as the altimeter goes, we're going to basically, for some time after startup, also use Welford's algorithm to manage current altitude. Basically, we're going to save that value off as static bias and subtract it from future readings. The altimeter attempts to read in feet above sea level, but we don't really care about sea level. We care about how high off our ground we went, so we zero that out on launch. Oh, sorry, real fast. Worth noting that if anyone here is deeply into IMUs, the kind of random walk noise and other noise parameters, we are not calibrating away. We would have to do that sequentially, and that was one of the things that would take too much time. So the state machine that we promised and we have that can detect launch. Basically, the algorithm somewhat follows this. We check for an acceleration above a tunable threshold for some amount of time. It's a pretty coarse threshold. Obviously, we go from almost zero acceleration to about 16 Gs in like half a second or less. It's pretty hard to miss that one. And so basically how high that threshold is and how many readings we need are tunable parameters. Landing detection works kind of similarly. We check for consistent, very low altitude. That one's also pretty hard to miss, right? So then again, how low your altitude is and how long that has to be true is also a tunable parameter updated in place. And then apogee detection, if change in altitude is negative enough, right? How negative, that's a tunable parameter, between some number of readings, right? Then we've detected apogee, right? This one's a little trickier. It's more nuanced to detect. So this is kind of the all eyes on apogee detection for the test flight. The number of measurements and like the descent comparator, how big that interval is, are the tunable parameters of that algorithm that we'll need to test. And then fault tolerance, like I mentioned earlier, we don't have two of every sensor, but we have two ways to get every source of information that's spread across the sensors. We can compare sensors. That's useful for future designs. What did we like? What we didn't like? How hard was it to get this one to work? We will check the sensors on startup, right? Like I mentioned earlier, if there's been something wrong in transit or manufacturing, then the computer will not fail by the time it gets in the launch pad. Again, we don't think it's going to check the status of each center, but we might do that just for the state machine, right? So in case something like that changes in flight, just for the state machine, otherwise it's probably not worth saving. And then open work following CDR, right? So the goal of this kind of list is things that, let's say our dreams come true and we get all this done. Anything that needs to be tied up is validated and done right at test launch, right? Some other open things that could not hurt the design we already have are sensor fusion algorithms, right? So if we have two sources of information, you can kind of denoise them or calibrate them, but then you can also denoise them against each other, right? That means we would be that would kind of streamline our sources of information and make our data more accurate. If we can compress more data, we can send more data. Right now, we're sending at 5 hertz with some assumptions about what the least significant bit is on our data. If we could send more, we would, right? So because of the antenna hardware that we've chosen, we have a really reliable and strong and wide signal. But it means that comes at the cost of not being able to transmit as much. So if we can make our data smaller, we can transmit more. Flash memory file system instead of using an SD card. The SD card modules have proved finicky and it's slow and also can damage the SD card with writing at the amount that we're writing. I mean, we probably write a couple, like 16 kilobits of data every like half second or so for the entire time the computer is on. And so aggressive writes to the SD card can wear it down quickly. If we somehow had time, we could look at advanced state estimation techniques or dynamic models of flight. And then scheduling optimization, right? So like I said, the CPU is extremely underutilized, not in a bad way, like in a good way, right? We have a lot of overhead room here that we could use to make this, even just everything that we have now, just run faster if we wanted to. And then after test launch, it's really pencils down for sure unless there's a bug that needs to be addressed, right? But at that point, it's too close to contest to bite off anything on this list. Now move on to the ground station.
Hi everyone, my name is Tan, and I'm currently responsible for the ground stations this semester. The ground stations is a combination of two main systems, the COS ground stations and the SRAT ground stations, acting as a two-fault tolerance, so we ensure that we get the data from the rockets reliably, but also experiment with our SRAT system. A little bit about the cost ground station system. On the far left side is the Yagi 3 antenna that we are using to receive data from the rocket. It will be connected to the laptop and running a vendor software to get the data and see the data live. On your right side, the right picture is the telemetry V3. This will sit on the Juno rocket and transmit the data from that rocket to the ground stations received by the Yagi antenna. Both were run on 432 to 445 megahertz, 70 centimeter band. A little bit more about the data of these hardwares. The Yagi antenna has an antenna gain of 5 to 8 decibel isotropics with 100 watts of power output, which around 50 decibels milliwatts. For the telemetry V3, it has a sensitivity of negative 111 decibel milliwatts with an antenna gain of 2.5 decibel isotropics. These data will be vitals for our range calculations later on, which I will show you next. So how do we validate our data? The formulas that we are using to validate this range of data is called link margins. And it uses the power received from the antenna minus the sensitivity of the telemetrons, to get the link margins. And we can convert the link margins into a distance with the formula, which I didn't include, should have included, but and we theoretically in free space range for this cost system, we are getting around 931.24 miles with a miscellaneous loss at 20 decibel and some loss for the connector around 0.1 decibel. For the actual space range, which means that the physical line of sight of the rocket before we lose the data into it is around 143.74 miles at 10,000 feet. And at the bottom is the formula that I'm using to calculate the theoretical actual space range. Let's get to the cost software. So we are using the ROS v1.922, which is the latest versions right now. And we'll be mainly using it for monitoring live data, save the flight data, and also replay it if needed for analysis. Next is the Student Research and Design Ground Station System. This is our main focus for this semester and the upcoming semester as well. The main microcontroller we'll be using is the TNC 4.1. We specifically chose this microcontroller because it has an SD capability instead of using the ESP32, which we had to implement another SD modules, which would cost us more money to buy. For the transceiver, we are using a LoRa 96, using a SPI interface to communicate with the TNC. And on the receiver side as well, we are also using the Yagi antenna, like mentioned previously in the other slides. And for the transceiving side on the rocket, we're using a Y antenna, which I will show the data of that antenna later on. The system will also be running around 428 to 431 megahertz or 445 to 440, which depends on IREC rules and also on launch date, where the other teams use certain frequencies, and we are trying to not using that same frequencies so we have less interference with them. These are some data into the hardwares. The LoRa, as you can see right there, is embedded with a chip, the SX1276, with a sensitivity of -148 decibel milliwatts. When 20 decibel milliwatt as well for the transmitter power output, and the default rate of it is around 19.2 kilobit per second. And we can also adjust that range up all the way to 300 kilobit per second. Right now, we are using the 19.2 kilobit per second, which equivalents to 17.1 data packets per second. Pretty fast. For the Y antenna on the Rocket, we'll be using a 6.5 inches cord, and be able to use that antenna for the 433 megahertz. The gain of it is also 2.15 decibel isotropic. Again, the range verifications for SRAD, according to the data sheets of the LoRa, it has a coverage capabilities of 20 kilometers. But we want to get deeper into that. The free space range, as I mentioned earlier, using the same formula but different data from the sensors, we got around 1240 miles of link margins, also using the same miscellaneous loss at 20 decibel. The theoretical actual space range is also around 143.37 miles, almost the same as the cost system, because this has something to deal with the line of sight, and the curvature of the Earth overall. Let's talk about the software for the SRAD ground system. The TNC on your top right there is using a C++ program, and it will retrieve the data from the LoRa and process it. And then it will give it to a backend applications built in Python. This backend will retrieve the data and process it, and then it will update those data onto a user interface applications that will be running on a local laptop and also a local host website that expand the coverage of those data, which I will mention later on. Specifically for the app, this is the current user interface of the app right now. It's updating altitude, temperature, and apertures, almost every data that we want, that we receive from the Rocket. For this version 1, we are seeing the capabilities of updating live data. We're also seeing the data being graphed live as well. The user will be able to fully manually control it, along with automatically control the range if the user want to. And it will be also be able to display the GPS coordinate. In the beginning, we were planning to use a map, but that costs a lot of power consumptions and memory usage. So we decided to go with a graphing GPS coordinate system, which simplifies the overall backend. For the local hosted web, we will be building the website using JavaScript and Fast API. We are currently researching on how to allow that website accessible to multiple users. This website also has the same capability as the app. It will update the live data, graph it, and also display the GPS coordinate. This is the full map of the SRAD ground station. The LoRa will receive data, give it to the TNC, and then the TNC is connected to a laptop that is running the back end of the applications. It will retrieve that data from the TNC and export those data into the local applications and the local hosted website. And it will increase the range of coverage of these data to multiple users. These are some of the telemetries that we are planning to send. The most vital ones are the BMP, which sends the altitude, the pressures, and the temperature of the rocket. We also care about the ADX cells and the LSMs, which send us the XYZ accelerations, and the BNO, which gives us the XYZ gyroscope data, along with the GPS, latitude, longitude, altitude, and the apogee of the rocket and the flight state. Overall, the total amount of bytes for this data struct is around 140 bytes, and this is optimized. The previous struct that we used has around 160 bytes. That is 15% more data, and we were able to reduce that amount of data to 140 bytes. These are the upcoming tasks for the SRAC ground stations. We're planning to develop a PCB design that connects the TNC microcontroller, and the LoRa together, so we can reduce weight of instead of using a breadboard, which is heavy, obviously. For the applications, the next versions, V2, we have a plan to implement the baud rate and the COM port editor. So when the user turn on the applications, they can manually edit these informations and make sure the applications run correctly on their machine. For V3, we will be finalizing the website and package the applications to run on multiple operating systems like Linux, Windows, Mac OS, you name it. I'll leave this testing to Jake.
So, to kind of get into what we have done in testing, the COTS flight computer has been, at least the telemetry has been tested. The graph is right here. This was from my personal L2 launch a couple months back, and everything seemed I compared it to other people's graphs online, and everything seems very normal and perfectly fine. The Easy Mini has not been tested, but there is plans to test it. The reason it hasn't been tested was that every launch that we finally planned to test it at got canceled, so nothing we could really do about that. But it is planned to at least launch before test launch in March. But I have pressure chamber tested both flight computers. They function perfectly. Basically, the reason is that since these are barometric flight computers, it will detect the change of pressure to kind of like kick on, and it will turn on. Basically, we put little Christmas lights, and it would turn on at its supposed apogee and its main deployment to kind of simulate turning on the chargers. But again, everything kind of went fine. To kind of go more into the telemetry, I would say the accuracy of the GPS was probably within like maybe 5 to 10 feet from where it actually landed, so that is very promising. The other thing I've done is battery drain testing on at least the telemetry. From 4.2 volts to 3.7 volts, we are getting about 31.3 hours of runtime. The battery might even be able to go lower than that, to upwards of like 75 hours. At most, the rocket will be on the pad for like 4 hours, and by the time it lands, we already know where the rocket is at, so it will be fine once it does that. SRI flight computer flight test is still open. That's just because we're planning on doing that for the during the flight test as a team. And avionics interference testing is once like the AV bay and everything's kind of put together, then we can finally start like moving, kind of offsetting wires, making sure like where everything kind of sits at to make sure they're not going to interfere with each other, and we can get good data from every single piece of computer. And then we're going to recovery.
Good evening, everyone. My name's John. I'm the recovery sub-team lead. So everybody else gets the rocket up to altitude. Recovery gets it back down. As you can see, takeoffs are optional, but landings are mandatory. Since PDR, our focus has been on testing and manufacturing. So we have successfully completed our parachute drop testing. We've then taken the data from that and calculated our descent rates and inflation times for the chutes that we plan to use. We've also finalized our design for the recovery bulkhead in conjunction with structures and avionics. We've also trained ourselves on parachute folding techniques and the attachment methods. different knot tying and how to actually Z-fold the parachutes and pack them into the protective bags. We've also calculated our black powder charge sizes for the ejection charges we'll be using to separate the rocket and deploy the parachutes, using both lower and upper bounds for the shear strength of our shear pins that will be holding those bays together. Here we have a basic flight path breakdown of the rocket, basically the entire timeline from launch pad to recovery. You can see that as it gets up to apogee, the drogue charges will fire, separating the rocket at the bottom of the avionics bay, deploying the 24-inch drogue chute that has a drag coefficient of 0.97. It will then come down at about 28.9 meters per second, down to 1,000 feet, at which point the main, primary, and secondary will fire, deploying the main chute, which is a 6-foot, 1.6 drag coefficient chute. That will slow it down to about 7.9 meters per second, and that will take it all the way from 1,000 feet down to the ground. You can see there we also have the basic design for the inside of the recovery bays, both for drogue and main. They'll use the same basic format. There will be U-bolts or I-bolts at both ends, with the shock cords attached using figure-8 knots and 1,760-pound quick links. The parachutes will be attached 5 feet aft of the forward bay using an alpine butterfly knot. These are both very good knots for withstanding lots of force on those cords. The alpine butterfly knot will attach to a 1,760-pound quick link, which will then attach to a 1,500-pound swivel. So if the parachute or the rocket begin to spin, it will not twist up the shock cord. It will allow it to kind of freely spin. Moving on. Here you can see a little more in detail of where recovery will sit in the rocket itself. The main will sit forward of avionics. The drogue will sit behind it, with the various charge cups sandwiching avionics around it. We will be using 6 shear pins per bay. These will be 440 nylon shear pins with a shear strength of 50 to 75 pounds each. You can also see a little more in detail the charge sizes. The main black powder charges, the primary will be 2.2 grams, exerting 50 pounds of force per pin. The secondary will be 3.23 grams, exerting a little over 75 pounds per pin, kind of nicely bracketing the range of shear strength for those pins. The drogue bay is much larger. The main bay is 14 inches long. The drogue bay is 40 inches long. It's not a totally hollow bay. It will have the motor in there. Comes down to an equivalent 33-inch bay. So here you can see our parachute testing. We used a concrete mass, the same as we did last year. It is a 47-pound mass. That was our initial mass. But with the sort of finagling with the rocket mass in order to meet our apogee, that mass has gone up. So we also tested it with some weights clipped to the top of that mass, increasing it to 67 pounds. And you can see here we have calculated the main descent rates to be between 37 and 39 feet per second. That is a little fast, a little faster than we've calculated. However, that doesn't factor in the drag of the block itself. The brick itself was only about this big, about 2 feet across. So the rocket itself will have a much higher drag, as well as the extended shock cords. Those will also have their own drag. So those descent rates will actually be lower than we've tested here on campus. The drogue chute itself did not reach terminal velocity, that 28.9 meters per second, but that's just because we only had 58 feet of drop to work with over at the Gateway Garage. Here you can see we have a nice little video here. I've made a compilation of our different tests. This is our 47-pound drogue test, then the 67-pound drogue test. Then we have the main with 47 pounds, and then the main with 67 pounds. And then this is another main with 67 pounds. And then this is a 12-foot chute that we decided to test that our mentor Doug very helpfully provided, but there was not enough fall time for that chute to fully inflate. For the black powder calculations, you can see these are the equations that we've used using the volume of the bay and the desired force on the bulkhead divided between those 6 shear pins. So with a 33.3-inch equivalent cylinder for the drogue bay and then a 24-inch bay for the main, we need about 300 to 450 pounds of force on the bulkhead to get 50 to 75 pounds on each pin. That brings us to those calculated masses, the 2.2, 3.23. The drogue primary will be 5.23 and the drogue secondary will be 7.6 grams, yielding the same force per pin distributed between each bay. This is a picture from last year's ejection test. Once we actually have the rocket body fabricated, we will be doing some aggressive ejection testing to ensure that they do separate with authority, as last year that was our main failure point that put Phoenix 7 feet under the desert. So we will be ensuring that this functions properly so that Juno will actually come back safely. Next, we have the snatch force calculations to ensure that the rocket will actually be able to withstand the force exerted on it once the parachute fully inflates and decelerates the rocket. This equation was pulled from a Naval Weapons Lab document. You can see the various calculations here. The CX is the opening coefficient at 1.8. The chute itself, the manual itself actually recommends a CX of 1.6, but we are over-engineering this a little bit, so we have upped that to 1.8, calculating for a worst-case scenario opening. The X1 is a force reduction factor, which I can show you later on in the appendix how we actually found that. The Q is the dynamic pressure at deployment, using the atmospheric density at deployment multiplied by the square of the descent rate divided by 2. And then that total force comes to about 370 pounds force. Our weakest component in the recovery chain is that 1,500-pound swivel at the base of the parachute, giving us a safety factor of 4.04. Very safe. We are very confident that everything goes to plan. This will be well within the range of acceptable forces. Thank you.
So test launch. So at our preliminary design review, we initially we're opting against hosting a test launch. And the reason for that was the risk of losing the vehicle and not having the resources to essentially rebuild it before launch. However, our amazing mentor, Doug, has offered to commit the components to replace the vehicle essentially in the event that the worst case scenario was to come to pass. So with that, we felt more confident in evaluating a plan for a test launch. So to manage these risks, we have 3 contingency plans and a ideal timeline. So case white be our ideal timeline, and our primary mission path, it assumes a perfect test launch at the latest on April 11th. Case orange is a contingency for a missed internal go-no-go decision by our final cutoff date, and that would consist of no test launch. So essentially, the first flight of Juno would be at competition. Cases green and black are contingencies in the event of a test launch that results in damage to the vehicle. So case white is our primary mission timeline at the moment. It aims to finish manufacturing by spring break, mid-spring break, and ground testing of the recovery systems soon after that. We've identified 2 primary launch windows. So a primary launch window on March 28th at Tripoli Houston South Site, and a fallback secondary launch window on April 11th at the Hearn launch site. Decisions to scrub would be made at least no later than 72 hours before the actual launch date. And the April 11th launch date is there in the event that timeline slip. It would give us an extra 2 weeks to, I guess, potentially still host the test launch. Failure to pass these go, no-go criteria or go, no-go deadlines would immediately result in the team following on to the case orange timeline. So case orange is the event that we fail our internal go, no-go deadline on April 11th. We would essentially finish whatever work that needed to be rectified that caused us to not pass that internal deadline. And we would focus on training competition members and having dry runs of assembling the rocket for competition. Cases green and black are in the event that we host the test launch at our latest fallback date of April 11th, but we do sustain damage to the vehicle. Case green assumes some damage, but it's limited to a certain component of the vehicle. Obviously, it's a little hard to, different components will take different time to replace or refabricate. So we took the worst case scenario of rebuilding the lower assembly, which includes the motor mount tube, as that is the most time consuming and difficult part of the vehicle to rebuild. And that would be scheduled to be completed by end of April. Case black is the worst case scenario. It would essentially consist of a total loss of the vehicle at our fallback launch date on April 11th. It is the worst case scenario. We would begin work almost immediately on repairing or reconstructing the vehicle, and manufacturing would continue on through past finals week into mid-May. Yeah, so the timelines for these were a little dense, so we did decide to add them to the appendix.
So moving on, we understand by taking on the plan of a test launch that there are a lot of risks, a lot of worries that have been attributed to it. So to account for them or to mitigate them, we've decided as a team to make an inventory checklist, which accounts for all the important parts of Juno themselves for each and every sub-team. As you can see up on the presentation screen, we have structures and avionics part, or the important structures and avionics part, and all of these parts have been accounted by either the team leads, by our mentors, or even through general excess inventory that we've had from previous years going on. And what's currently pending is our recovery equipment replacements, as you can see. So currently for our recovery hardware replacement, our intended or needed budget is $436.99. This budget or needed budget accounts for all of recovery, including the parachutes, the mechanical linkages, the shock cords or Kevlar, as well as other miscellaneous recovery items. So yeah. So moving on to our final point, thank you guys for being here. We just wanted to take some time to have a few specific thank yous. We wanted to thank our two mentors, Doug for being here, as well as Randy, who's online. We really want to thank Randy for his contribution to our motor, buying our motor as well as intended motor hardware this project cycle. And we really wanted to thank Doug through his support through both fabrication equipment as well as his commitment to the Case Black timeline. These two are the whole reason we as a project team this cycle are so ambitious as well as so confident with our testing and manufacturing plans, and their guidance has been utterly invaluable throughout this entire design process. And then moving on, we wanted to give a few more specific thank yous. We wanted to thank Alfredo Hernandez, the previous chief engineer. We wanted to also thank Isabella Deacon, the previous project manager. Without your guys' support, both for logistical issues as well as therapy, we would not be half as successful as we are right now. We also want to say a few thank yous to some faculty as well as alumni that have provided support through our project cycle. I want to thank Dr. Hamami, Gustavo Santana, Haley Stafford, Brandon Broadway, Robbie Desai, Alex Blick, Eric Lopez, Christian Rossi, Kelly Graham, Jalissa Martinez, Christian Berend, and Emily Humble. And not just these alumni, but all the alumni and STLs that have contributed to this project, as well as our members that have been so active this cycle onwards. Thank you for attending our general meetings, as well as our testing and manufacturing events, especially since we don't have a lab. Thank you, Doug, for providing your garage for all the manufacturing. We are so thankful for the support you've provided both this project cycle as well as previous project cycles, and we hope to have your guys' support throughout Space City Rocketry's presence in AIAA. So moving on to questions, if I can get all the STLs up here, we can start on the question session. And like I mentioned, if you guys aren't able to answer your questions or if you'd like to provide answers later on, we'll be going back to the first slide, and that is the QR code you guys will have to scan to submit your questions. So yeah, thank you.
Are you only taking questions through the QR code?
No, this is mainly for people who want to submit their questions just in case they have to leave, or if we have to end at some point and you guys still have questions, you can scan this and submit your questions. We'll be having around a 30 to 40-minute question session right now. So yeah. Yes.
So I guess I'll start with where y'all ended the worst case scenario timelines. So could you reference back how much time are you giving yourselves to recover from like the worst case scenario? So the case black, like, are you also including shipping as well as manufacturing times for specific things? Like I know the fins are gonna have a lot of layup times, like things like those. What is your worst case scenario?
Worst case scenario, we are still taking into account delivery times. Because of that are substantial items that have a large delivery time we already have in stock, such as the airframes, the structural components as well. The only thing we are worried about is recovery equipment, but that is something we intend to purchase beforehand, a significant amount of time before we do our test launch to account for the delivery time. So yeah.
Do y'all the date of if the rocket is not ready by this date, we are not competing?
If the rocket is not ready for IREC? Okay. Ideally, we have the plan of 3 weeks beforehand as a go, no go for our IREC competition so far. Yeah. Sorry, this is gonna take a while. We understand it is also very difficult to see here. It's very, very tiny. We have the Gantt chart linked as well in some of the appendix. So yeah.
Emily.
So if you fall into case black and you have a total loss of vehicle, would you rebuild the rocket the exact same way?
We would try to. We tried accounting for that in the inventory as well as through our rigorous documentation process this time around in case of the case black occurring. We would want an exact replication of Juno through both our airframes, our parachutes, and our process of manufacturing.
So what if case black was caused by a failure of, let's say, the structure or the way you've got your avionics wired? You don't really have time built in to get to the bottom of the cause, so like a redesign. So if that were to be the primary cause of the failure, in a way you're saying we're going to do the same thing, so the expected result would be failure again, right?
Okay. Accounting for that, we'd want to take some time to be able to deliberate. We have, if I'm not wrong, some time for deliberation for the test flight itself. And because of that, when I say we want to recreate Juno, I mean we'd want to be able to replicate as close as possible to our progress report as well as our technical report submissions, but we will account for our failure methods as well. Any point we see a failure through our data collected through avionics, or as well as our assumptions through our procedure, our checklists, procedural tasks as well, we would account for those kinds of failures.
Just to add to that, I guess. So obviously, we would have a after action report to kind of determine the failure mode. In the event that the structure was the failure mode, that's kind of at that point we would not be launching again because the components we have guaranteed as replacements are the exact same components. And so in the event that it was a structural failure, that's kind of we can't really do much about that. In the event it was like a recovery or avionics failure, those are generally like the last parts of the rocket that are actually built. So we do have time to sort of redesign those.
Going with case black is very contingent on the root of the failure. If it is the rocket itself that failed, I agree with you to not rebuild the same way, but if you can determine something wasn't plugged in and it should have been plugged in, that's very different. That's an operational mistake. But it would just be, it just takes time to determine what happened and get to the bottom of that I want to see built into this schedule.
Yeah.
Yeah, I'll keep looking about case black. So how does this timeline compare to what it's looked like to assemble the rocket so far? So you guys have definitely not been under schedule pressure up to this point. How will that change when you guys are under schedule pressure? And I think you guys mentioned you'll also do the finals some other grants. So I guess I'm just curious how you guys got to the rebuild the rocket.
And generally, realistically, I think the majority of the failure would be heavily reliant on primarily the recovery and the structures team. So specifically, how many members do y'all have? Could you support a reduced timeline? Could you support that with finals? Be thinking about like team health and your grades. Like, can you support that still?
I can kind of answer that. I will say, having experience from last year being structures, we kind of built the last rocket in 3 weeks, which is also the worst case timeline. And that was with like me and Alfredo mostly in the lab. This year we actually have a lot more structures involvement, as you saw. Like we had Oscar, Henry's helped out, Antonio. We have a lot more support as far as structures and people we are training to get more involved. So it's definitely been a lot smoother of a path. We've been getting like structures tasks done in a couple hours that day versus, spending all night in the lab, trying to figure out and, deliberate things. And I think the process has gone a lot smoother versus last year, and it comes with the experience as well as much more support from members as well.
As far as recovery goes, a majority of our components are COTS, and with the replacement items budget, ideally we would have those components on hand prior to the test launch. So remanufacturing the recovery hardware would be very quick.
I guess I'll just add in, avionics is kind of very similar. Since the majority of the recovery system or the import system is the COT system, it's just repurchasing, which we have accounted for. The SRAD system, I mean, we just reiterating the just telemetry package and like stuff like that. So by the time that we're doing test launch, unless there's like some weird hardware stuff, we already have all the files, we have all the code. So we could just reorder everything and everything will come in just fine. And there's probably no development, but again, that's if like we didn't screw up somewhere and like have to redesign, but like that's.
And it's also worth noting that we do have some of that hardware on hand already.
Yeah.
We not only could we pre-order, we have pre-ordered. So
yeah. And the nice thing is about PCBs is you typically order like 5 when you pre-order them. So you always have extras if so.
Love a run.
Yeah.
Thank you.
I have a question for recovery specifically. So the majority of the UH rocket failures have been because of recovery. And it's not necessarily because of a lot of the testing that you showed here today, but it's mostly because of things like the parachute getting wrapped up in the cord or having too many like rubber bands wrapped around the cord to keep the parachute contained. How are you testing that? Like what resources are you using to determine how best to keep the parachute nicely bundled, but still actually get it deployed, return the rocket safely?
Through the drop testing, while we were dropping it off the testing site, we were practicing folding and packing the parachute the same way it's going to be packed at competition. Obviously, we didn't have 40 feet of shot cord because that would be almost our entire testing height. But those cords, the Nomex bags that Doug has gracefully provided for us, have elastic bands around them for flaking, so we wouldn't need to use rubber bands or masking tape or anything like that. And given our experience with that kind of parachute protective equipment last year, the cords do deploy very smoothly when you do a Z-fold sort of flaking into those elastic bands. They're almost tangle proof because as the shock cords extend, they are pulling out one flake at a time from the bands, and then the parachute itself is Z-folded around the gores. So especially given our parachute testing on the 7th, it was very smooth. We didn't have any parachutes come out tangled. They came out and inflated very quickly. So that training has really helped us be really confident in our methods to ensure that that doesn't happen.
I wouldn't say it's a 1-to-1 analog though, because even though that's a good test, you're dropping a parachute from a block and the parachute's already out in the wind. It's not in a tube like it will be on the rocket. So I mean, we've seen at the competition, like the rocket, the parachute just gets stuck inside the tube and never comes out of the tube. So you've still got that risk.
That also factors into our ejection testing, where we intend to eject with authority. Basically, that the ejection charge will be sufficient to force the body all the way to the full extent of the shock cord to ensure that that doesn't happen.
I have a question, and so I came in the first 15 minutes, so maybe this was answered already before I got here. But you mentioned in the propulsion section that when you assembled your fins, you noticed that they would cause your apogee to be lower, and so you had to change your motor. Is that a correct readback?
Yes.
Okay. How was that decision made? Why did you decide to change your motor rather than change your fin design?
So originally we had our idea for making the fins was using tip-to-tip layups. However, we got a lot of feedback on that from our PDR, from alumni and from our mentors. And sitting down with our mentors and really discussing through our options, the specific method, essentially creating a composite structure of just the fin, how that work out essentially changed the leading and trailing edges of the fins. So that affected the aerodynamics by that much.
Not a weight thing, is it, Brett? Yeah.
Yes.
And you don't think you could have compensated by beveling or tapering with the fins you have?
We could have, yes.
Okay, so why did you decide against that and decided to change your motor?
Okay, so mainly for that, not specifically that incident, but essentially incidents of that sort, we do expect the avionics bay, for example, to weigh more than obviously what we're factoring now. And essentially to account for that, I guess, margin in the design, we'd rather add weight to reduce the apogee rather than try to scramble to like reduce weight to increase our apogee. Hence our selection of this different motor.
Okay, and then remind me, how does that change? Because your goal is, the competition rules, right, is you try to hit exactly 10K?
Correct.
So how was that trade-off made, knowing you're not getting, so it sounded like you were overshooting by some feet, but now you're undershooting by some feet and not getting closer to 10K, or did you get closer to 10K by making this choice?
By making the choice of switching the motor.
Yeah, so you have a new apogee now, it's
Right.
lower. Is that any closer to
It's
10K?
it's higher. The new apogee is higher, and the reason for that is to account for design changes like that. So essentially, we wouldn't have to, scramble to change tiny little things to increase our apogee. We'd essentially add weight, which is a relatively easy thing to do, and that would reduce our apogee. So that was the decision that went. That was the thought process that went behind making that decision.
Okay, thank
You have any questions, Doug?
Like to think I'm pretty up to the minute, caught up with everything, considering I've had a lot of individual hands-on experience working with team members. So I guess to visit, and this may be something the alumni may be interested in as well. So if we're looking at these Gantt charts now. I know there are a couple of items that I believe we're already a little behind on for case white. Is that correct?
Correct.
From my memory. Okay. I remember reviewing some things and thinking, okay, this really shouldn't take this long. So we can make up some time there, but just wondering if the leadership and structures is aware of the fact that we're already kind of lagging and have some work to catch up to those points already. And I mean, we're talking about 1 or 2 days at this point, right? But that's just like, okay, well then it might be a week by the time we actually get to do those things. So I guess it's less of a question and more of a heads up to stay on top of that, because those things can start to cycle on top of you, right? So be aware that falling behind can happen, and as long as put together a plan to recover from it, probably okay. That said, I do believe a 3-week timeline to build the rocket from scratch is more than sufficient. The largest delay is the airframe construction, and the largest delay there is just the curing time on the epoxy. I believe we have all the power tools and cutting methods refined, and we know what to do there. Yeah, but good presentation, I thought, overall. And again, I have less questions this time than I did before because I'm more up to date on everything that's been going on. And thanks for inviting me to do that too. Very interesting. I've had a lot of fun getting to the team.
Is there any concern about potentially over engineering the fins? I don't recall us ever having issues damaging our hardware before attempting to cut the fiberglass or the carbon fiber. So I'm just trying to understand how much thicker are these fins? What are we doing so differently?
What modulus?
A large part of the overdoing the strength of the fins comes from the calculator that they're requiring us to use for IREC. With that calculator, it means that a lot of designs in terms of the fins, in terms of the flutter velocity, it's requiring a lot more to get basically to what the calculator wants. Yeah, so well, it's requiring still a factor safety of 2, but it's like calculating that it's it's requiring a lot more to get to that factor of safety, I guess. To the point where a lot of tried and true like rocket kits, like the Wildman ones, the fins on those don't pass at all. Which I mean, those have been flown like hundreds of times. They're purchased kits, they're engineered kits, and they don't even pass that calculator. So trying to fall within what the competition wants, obviously we're going to engineer fins that are going to pass that so that they don't question us more than we need, and have to make last minute decisions. But yes, the fins are kind of over engineered with 5 layers of carbon fiber on each side. Um, they are very strong fins. They're kind of built like a tank. I wouldn't have personally put that many layers, but it's more of trying to uh, reach what is required for the competition.
So you mentioned a lot of testing you want to do across the various subsystems. Have you started any testing already?
Well, we've done some testing through parachute testing.
Yes, parachute testing. Amazing. Also, what I was thinking of mostly was the structural testing, like we want to do with Dr. Hamami, the test, which is awesome. But I'm just, I guess because you're damaging your own manufacturing tools, like that's a good sign. But I was just curious if the tests don't go well, what are you going to do if the tests don't go well?
I mean, I doubt that the tests won't go well, especially with the calculator having us overshoot so far. But that's why we're trying to get that test done as soon as possible. So whenever it comes to manufacturing the fins, we can make like the adjustments that need to happen. Obviously we have the core for the fins, but when in terms of like layups or how we do the layups, that can still change a lot whenever it comes to doing the operation. And a big thing whenever it comes to doing the test coupons was getting experience. So we can also improve upon that whenever it comes to actually doing the realistic layups.
Yeah, I'm less worried now that you've given the information that you're destroying saw blades with your fins. But if, like, anytime you have a house-made material, the testing is not like, oh, we're just seeing this like to have data, but we already know it's fine. It's more of like a real, this could fail, and you need to plan in like, what are we going to do if it fails? So with the tests, I'd like to see some clear documentation of what is a pass condition, what is a fail condition, what number are you looking for to prove that you are good or not just curious numbers we collected. So I'm less stressed now that you gave that information, but I think you should still define that for yourself.
Yes, and I really do think that's where the competition they're trying to move towards with having you give a shear modulus of your fins to where it's like you have to actually figure it out and like know that number to have a reliable number versus estimating or saying like, oh, it's probably this, versus now we're actually have to doing the testing, getting a realistic shear modulus based on a test coupon that we created the same way as we would create the fins. So I think we're trying to do that as best as possible.
Okay, but your number you're looking for is the shear modulus. That's what you're testing for.
Yes, specifically because our fins are using 2 different composite materials in combination. Very hard to actually calculate that based off like different materials versus like a known number that you would get for just like using just straight only carbon fiber or only fiberglass.
Okay, thank you.
Dita, do you have the calculator on your, I know it's not in a slide, I don't think, but do you think you have that? Pull it up. I think we could work backwards from that calculator and pull the exact shear modulus minimum that we need.
We might have forgotten to put it in.
Is it on your laptop?
It's not a slide, that's fine, but I think we could do that.
Okay.
Yeah, knowing your theoretical versus actual would be a awesome thing to discuss in your technical report.
Assumption that the calculator does
Yeah.
make that the shear modulus of carbon fiber and fiberglass are equal.
Mhm.
Which is most likely not true.
You can prove the competition wrong.
Yeah,
Way over here.
hopefully so. That is also why we had multiple test coupons of the fiberglass and the carbon fibers, so we can prove that as well.
And just another point on testing, I know at avionics you had a very dense section about your SRAD flight computer. I think this was the wrong forum to discuss that. Like just in general, I think you guys need your own CDR with some real technical experts who are versed on software engineering and ground up electrical design. Because I feel like I am not qualified to give you a proper response on whether that was good enough or not. So I think you guys should do another CDR for just your own system because it's complex enough and you're in the details deep enough that you deserve a thorough and fair evaluation from people who actually know what you're talking about. So I would say that's good presenting stuff, but I don't think we were able to give it a fair evaluation today. That makes sense.
So I was looking at those, I also got here a little late. Y'all are planning to bring 7 people, minimum of, or 8 people to the competition? Well, I see there's 9 of y'all up there. I'm not. To follow up with that, are y'all have a idea of bringing members there to, what are y'all doing for the new tenders, for the new team that comes after y'all?
Well, for example, one of the reasons we wanted to do a test launch was to give our new members who were extremely active the cycle around the opportunity to have an IREC experience just in case we aren't able to take them to IREC within our estimated budget.
What's the maximum amount of members you want to take? I missed the number.
Ideally, we would want 4 rooms and we would be able to take more members. But right now, within the budget, being able to collect $500, around a little more over $500, we'd be able to take 8 people for 3 rooms.
And then I think I showed up too late for your budget slides. You might get around.
Yes. Yes.
I have my last question. For the whole team, I think John mentioned your leading theory of why last year's rocket failed was a black powder issue. Does the team agree that is what caused the failure last year?
There's a couple of theories. The leading one is a failure to eject, which could be caused by a couple of things. There was the Raptor, the CO2 assembly, potentially not filling with gas quickly enough. There was also the wiring harness, which we theorized may have vibrated apart, leading to the black powder charge either not going off or potentially being too small to eject the. There was another theory that the shear pins may have lengthened due to spending so long in the container and warming up. They may have stretched rather than sheared, which would have required a larger charge to actually separate. Obviously, without fully recovering the rocket, as half of it is still in the desert, we can't verify exactly which one of those that it was. But by mitigating as many of those potential causes as possible, using screw locking wiring harnesses, using authoritative ejection charges, essentially foolproofing the system, for those potential failure modes that we theorized may have happened last year, we can ensure that we have a better chance this year.
And that was the second half of my question is whatever theory you're going with, understanding it's an assumption, or maybe it's a series of assumptions. Does the team feel confident you've mitigated that thoroughly to not repeat?
I would like to mention kind of like based off the data we got from the telemetry. I can say for certain that the CO2 did go off because we did see a pressurization of the avionics bay and showed the spike of that we typically see in like older Shasta data and stuff like that. So the CO2 went off. But the thing is we never saw a second spike, which we were expecting for the black powder charge. We don't know, and again, we don't know why that might not. So like John mentioned, like I think the assumption of under pressurization of the CO2 is very possible. But we are theorizing that the black powder didn't go off, but we're not entirely sure. The other kind of main mitigation, which may not have been very important, is that I noticed it during my flight and during my telemetry data, there was no pressure spike during my flight of the telemetrum, and that was because the way that me and Dita, and I noticed it on his as well, is that we seal off the avionics bay.
You shouldn't have any leakage.
Yeah. And that was just an assumption before me and him did our flight. I didn't even notice until we did our flights on our personal rockets. So now the kind of goal is to just contain that avionics bay so nothing gets leaked out. I actually noticed whenever I was looking at the old photo of the recovery, the recovery test at Hamfest, you could even see like gas coming out of the vent holes of the or the not the vent holes, but the screw holes of the yeah. It's just something we just never noticed, but that was because we just didn't know better at the time.
And so that's an entirely new failure mode. That is, everything worked, but you failed to contain your pressure to the proper chamber, and therefore your recovery did not deploy properly.
That's something that we've also accounted for in this year's design. The wiring harness, the wires from the avionics bay to the wiring harness will be permanently mounted and sealed. Like you were saying, to prevent any gas leakage into the avionics bay.
We plan on using just like probably a stronger connector, but me and Dita have used like JST connectors to kind of connect the bulkhead to the main avionics wiring to kind of just transfer that. We'll experiment with different connector methods, kind of create a stronger bond. But I mean, it's just making sure that bay is sealed and will not get any pressure inside.
Yeah, and I don't know how much. I mean, that's all good. I want to make sure you guys are taking extra caution with that. You're focusing that on, because I think my main takeaway from this design is it's good but generic, and I don't see an iteration. Knowing last year was a complete loss of vehicle, I would have expected more of, we think it failed this way, therefore we made these changes this year in this presentation. And just something else that we did in my year was not only sealing with connectors, we did a similar like a plug connector. So that's good news that you're doing something like that as well. But we also sealed with lithium grease, like around the edges of the fiberglass bulkhead. Like we pressed grease into the crack to prevent the air from going through. So something like that, or something similar to seal up even like the thinnest of gaps might be of use. Something I would like to see on your flight readiness review. I think you can do something simple like greasing to help with that. And that's my final question. I think you guys presented very professionally today. I've said this to Shrusti and Dita that your contingency planning is extremely mature. And I think actually if you do lose the vehicle, you have a really strong chance of rebuilding and relaunching at competition just because you put in the work right now to plan that. So kudos to you guys.
Yeah, when y'all do your test launch, let us know.
First, competition cost requirements in terms of the sensibility are different for subsonic and supersonic flights. I believe it's 7.5% for subsonic and 10%. I remember that you guys are like hands-on agreement. So how does that, what is your, is that similar looking like? And how does that, fit in with that, like, considering, how specific?
Our current stability in percentage is 10.5, I believe. 10.5. So yeah, we are within that margin.
Just to follow on that, thought a little bit though, I believe the RAS arrow number does have you going supersonic. And so of the three, I know we briefly discussed this on the phone the other night, so I was wondering if you addressed that or had any thoughts, because as was mentioned, the requirements do shift. And I can't speak for what the safety evaluators will say. But I do know that I know who they are, and I know that they are more inclined to follow the RAS arrow numbers when you start getting transonic and supersonic. So one thing I would be prepared to have come up, especially in the next round of safety reviews, is for that number to jump off the screen at them and for them to ask about whether or not we have, I believe, 2 calibers of stability is warranted for supersonic flights. So I don't remember the percentage, but I think I remember it would be 2 calibers. And I don't believe we are there now.
I believe
you
we're
can
at
move some ballast around and
2.02.
achieve that peak, but
Yeah. With the additional ballast, our stability would go up and our maximum velocity would go down as well. So I believe with our current assumption, correct me if I'm wrong, Liv, we're at 11 pounds of ballast, and that would bring us down to Mach 0.7. So
okay.
yeah.
So we're
Yeah.
almost out of that discussion. Okay. And then secondly, and John, you and I again talked about this, so but maybe to put it a little bit more on the record for everybody else, on the testing, on the recovery charge sizes, are these where we intend to start testing from and go up from there until we see the desired behavior in testing? Or are these where we're just hitting our estimations and that's what we're going?
So with last year's testing, I intend to kind of do the same thing where we have our planned charge size, but the initial testing charge, we intend to do a 20% safety margin. So if the initial charge is 2.2 grams, we back off 20% and start there and see what kind of data we get back. I intend to construct a scale to put behind the nose cone so we can measure the sort of ejection velocity of the upper stage, so that we can really kind of dial in those charge sizes. But no, I don't intend to start at the maximum charge size. I prefer to start with a more safety oriented, less than that max charge size, both to have a wider range of testing data, but also to ensure that we don't bombify our rocket.
So I think the charts are really good. One theme that I've noticed though is where is the requirements that the IREC documentation puts on you, and how does what your design shows or the things you have on your charts meet those requirements? So that's not something that I expect you guys to answer right away, right? Because that's probably going to take some time, but I'd love to see at some point you guys go through every single thing on your requirements document and say, this is how we meet that, and these are the points we expect to get if we were grading ourselves against these.
And I can just give you an answer for the descent rates. Under drogue, it's no more than, I believe, 110 or 120 feet per second. And under main, it's no more than 37 feet per second. So with the calculated rates, we fall well within that at 94.81 under drogue and 34.6, if I'm remembering my conversions right, under main. Obviously, our tested data tested higher than that, but like we said, the drag of the actual rocket body itself will further back us off of that.
I can answer for avionics. So a lot of the avionics stuff has been kind of based around the rules. Like the COTS flight computer, it is required this year to have a 7-centimeter transmission. Just as the COTS main computer, that's just the main requirement. They also gave us a range of like frequencies that we have to adhere to. I did list them for the COTS and the SRAD because it's different depending on which system it is. Some other things I did not add is like we have to use within 22 gauge or lower wire for our kind of wiring harness. And like the power output, I believe has to be, depending, again, it depends on what the range is. I believe it's like maybe 200 milliwatts to maybe underneath like 500 milliwatts or something.
Yeah, I appreciate the answers, but I guess what I'm getting to is like you can rattle them off for me, but I'd love to see a document where you show like this is the requirement, this is how we're meeting it. Yeah.
We definitely designed our vehicle with those constraints in mind, given I'm sure the sub-team leads could rattle off like for a good another 10 minutes, but that's absolutely right. We should definitely have a compiled list of how the requirement and how we meet them.
Yeah, I'm sure y'all are working towards those. It should help us to see it.
Kind of along the lines of that, I would also like to see a chart of all the items in the recovery chain, their working load limits, and that number compared to the snatch forces that John computed. I know he identified, I believe, what we said was the weakest item, but I think it would look good for the final report as well, for the technical report, to have all those items listed out and then compared.
If you go to the recovery timeline, I believe I do actually have them on there. Yes,
the 1,500 pound swivel, I think you said is the weakest.
Yes, right. You can see each component does have its structural limit listed here, with the exception of the U-bolts, because I think we're still waiting on some FEM for those.
Okay.
Very quickly, first of all, some of the CDR. One big thing is that the facility does close at 9 p.m. So if you have a question, please ask it at all. They're not able to get through before 9 p.m. Please put it in the question form or forward the executives officially. We'll make sure that they answer those.
So if I want to go to IREC, or like say you want to go to IREC, are we gonna need more money for that?
We are. We hope.
Budget where we are essentially asking for more money to have an extra roof so that if more people want to come, we have that already budgeted. Okay.
And also, the more involved members are, we do take that into consideration of who we want to bring to IREC. So yeah.
Have you, I guess one last thing, so on the travel budget, have you included Randy?
I believe Randy will be renting his own RV, so you got it covered.
Yes, so FORs are usually expecting the teams to fund their travel. So, okay, well, then that's the range. Yeah, okay.
Yeah, right.
Okay, I believe now that it's 8:57 p.m., that is the end of our CDR. Thank you so much, everyone that can make it both in person as well as online. Any more questions can be submitted through the QR code form in the first page, which we'll go to again for 2 minutes. And yes, thank you so much.